Hello, welcome back. So, we're on to chapter 5 now, the first part of chapter 5. And I like to swim, I like to snorkel, but I don't know how to scuba dive. Tell me, will this work? Say, what if instead of scuba diving, if I just had this really, really long snorkel, like a 100-foot long snorkel and snorkeled really, really deep? Will this work? And the answer is no, it won't. And the reason being is that for every 33 feet of water, 10 meters of water, that's in about an atmosphere of pressure. So that means that there are about 3 atmospheres of pressure. Why is this pen not working? So there are about 3 atmospheres of pressure from the water on my lungs, plus then another atmosphere from the Earth itself. And that will cause, there we go. This is, so you have 3 atmospheres here, and then 1 atmosphere there. That means my lungs, there's my lungs, it receives a total pressure of 4 atmospheres. So if my lungs are under a pressure of 4 atmospheres, and the end of the snorkel up here is at 1 atmosphere, what's going to happen? If I try to breathe in, my lungs will collapse. All the air will be pushed out of my lungs. And that is because flow always goes from high pressure to low pressure, or high temperature to low temperature, or high concentration to low concentration. So in this case, the depth will force the air out of my lungs back up into the atmosphere. So this is a bad idea. So pressure, you're probably feeling a little bit of pressure. What is pressure? What does pressure mean? Pressure means force divided by an area. So something, a common unit we use is PSI, pounds per square inch. So a pound of force over the area of a square inch, a pound per square inch. And there are other units of pressure. There is atmospheres, I've already used that one. The SI unit is called Pascal. That's a Newton per square meter. It's not a very strong force, not a very heavy pressure. There's also millimeters of mercury, or torr. So 10 feet of water is about an atmosphere of pressure. 760 millimeters of mercury, or 76 centimeters, which is equivalent to about 30 inches of mercury. That's an atmosphere. That's an atmosphere of pressure. An atmosphere is the average pressure of the atmosphere at sea level. In sound waves is a change in pressure wave in your ear. So sound is a pressure wave. So let me talk a little bit about different laws. So first one here, talk about Boyle's law. Boyle's law means, well, one way you can write it is P1V1 equals P2V2. This, you can also write it as pressure, this P, this alpha, that fish-looking thing, that's lowercase alpha. It means proportional. Pressure is inversely proportional to volume. So that one means when pressure goes up, volume goes down, or when volume goes up, pressure goes down. It's kind of like how much fun I have versus my bank account balance. Let's say I'm having lots of fun, I'm traveling, I'm going out to eat, and I'm going to special shows, my bank account balance tends to drop. What if I am staying home, watching Netflix, eating crock-pot meals, my bank account balance goes up. So that's what I mean by inversely proportional. Charles' law, the volume is directly proportional to temperature. So that means when one goes up, the other one goes up, and when one goes down, the other one goes down. So this is how hot air balloons inflate. I know that we don't have them in Hawaii, but a hot air balloon, you have like a basket with a droopy looking balloon, and then you heat it up, a flame, and then what happens is the balloon blows up. And then due to buoyant force, the balloon can then rise. So that's what a hot air balloon, that's how it works. So it's directly proportional. So, okay, and let me introduce another thing, is absolute temperature. So temperature, what temperature is, I mentioned this before, temperature is a measure of how fast things are moving in an atomic or molecular fashion. So what happens when things don't move? That's absolute zero. When things don't move. And we'll talk a little bit about it later. It's it means average translational kinetic energy is temperature. So translational, so I can move my hand around. So this is translational motion. What else can I do? I can rotate it. This is rotational energy. What else I can do? It can vibrate. I can vibrate my hand. This is vibrational energy. So the way that works, so temperature is motion here, is translational kinetic energy. And so if you wonder how how microwaves heat up things, so you put cold pizza in the microwave and you get warm pizza out. So this is what a water molecule looks like. So oxygen, 2 hydrogens, it rotates. When you put it in a microwave oven, you cause the rotational energy to increase, and then water molecules moving around, they rotate and they smack into each other, and then they get more translational energy, higher temperature. So that's how a microwave oven works. At absolute zero, microwave oven wouldn't work. You would have water molecules sitting here, and they're still rotating. Even at absolute zero, they rotate and they vibrate a little bit. It would just rotate faster, but not move anywhere. So, but it's really hard to get to absolute zero. It's very, very, very difficult. NASA just recently did it in space, actually. Okay, so Kelvin is absolute temperature. So and you can see it doesn't have a degree sign. So no degree Kelvin, it's not needed. So degree Celsius, it's a relative scale. Kelvin is an absolute scale. So meaning Celsius relates to something. 0 Celsius is when water freezes at 1 atmosphere pressure, and 100 Celsius is when water boils at 100 at 1 atmosphere pressure. So what is negative 100 in Kelvin? It's 173. Okay, so Avogadro's law, volume is proportional number of moles. You're probably familiar with that if you've ever blown up a balloon. So if you put in more air, the balloon blows up. You put in more moles of air, the balloon gets bigger. That's Avogadro's law. There's also Gay-Lussac's law, and let's just talk about what's important, the ideal gas law. And this is the ideal gas law. Pressure times volume equals the number of moles times the gas law constant times the temperature, and the temperature has to be in Kelvin. So gas law constant is actually the Boltzmann's constant times Avogadro's number. So R is actually 2 different constants multiplied together, Avogadro's number and Boltzmann's constant. That has to deal with, we'll learn about it more in thermodynamics. But okay, ideal gas. The other thing, an ideal gas, this is kind of an imaginary thing. Gases under certain conditions, low pressure, high temperature, may act ideally. The ideal gas, an ideal gas has no volume. The particles themselves have no volume. There's no attraction between the gas particles, and it's not real. It's a made-up sort of kind of like a fashion model kind of way of a way a gas should behave. So it never works exactly that way, but it works pretty well. So ideal gas law, and this is, like I said, it's derived. We're not going to go to the derivation. Let's do this for an example here. So calculate the volume occupied by ideal gas by 0.845 moles of nitrogen at a pressure of 1.3 atmospheres and a temperature of 315 Kelvin. So do this. Look at PV equals nRT. I always start with that. Then we're going to solve for volume. So you solve for volume. You can just, it's fun to do math this way. Boop. So solve for volume. So then we put in the parts. Moles 0.845 moles. R is 0.08206 liter atmosphere over mole Kelvin, and temperature 315 K, all over 1.37 atmospheres. So if you look at the units, moles cancel, Kelvins cancels, atmospheres cancels, and you're left with liters, and what's that? Then you put this into your calculator. And let me see if I pause it properly this time. Okay, hopefully I paused properly this time. You might have seen it didn't work, so you got a good show of what I do when the lights are off last time. Alright, so 15.9 liters is then the answer. That's how much gas it occupies, how much volume this ideal gas would occupy. This next one here, ideal gas. So it doesn't matter what gas it is, it's an ideal gas, they all behave the same way, ideally. So half an atmosphere, volume is 50 liters, temperature is 50 degrees Celsius. How do you solve this one? PV equals nRT. N equals PV over RT. Pressure is 0.5 atmospheres. Volume is 50 liters. Temperature is 50 plus 273. So don't forget that. That's a common mistake. And then R 0.08206. And you put that in your calculator. And if you want, you can do certain tricks here. Like if you look at this one here, you can put 25 for that if you want in your calculator. I'll just go ahead and, because 0.5 times 50 is like 5 times 10, so then multiply over, that's 25. So, or half of 50 is 25. That's another way we can look at it. So I'll just go ahead and put that 25 over quantity 50 plus 273 times 0.08206, and you get 0.934, which is about 1. So it's 0.934. All right. So the next thing is I'll show you a derivation. So PV equals MRT, and molarity, moles per liter, equals N over V, number of moles per liter is equal to pressure over RT. And then if you look at it this way, density is equal to so molar density, so the amount of moles per volume, that's N over V. That's the inverse of molarity. I'm sorry, that's right. Actually, that's right. I'm sorry. Times the molar mass. So density times the molar mass gives you. Oh wait, what are we doing here? So molar density, moles per liter, times grams per mole gives grams per liter. Density in grams per liter. Okay, that's what we got. So grams over liter is density in that. So that means that density over that is times the molar mass will give you pressure molar mass over RT. So, and there we go. So we're going to use this equation here. The density is the pressure times the molar mass. Molecular weight is the other thing I like to use to say. Molecular weight. It's like carbon dioxide is 44 grams per mole. And then RT. Okay, so pressure. So I just wanted to give you an idea of different units of pressure. 1 atmosphere is a common point. 760 millimeters of mercury, I mentioned that one. 10 meters of water. 14.7 psi, and also 101.3 kilopascals. Kilo is 1,000, so 101,300 pascals. Okay, calculate the density of nitrogen gas at 125 degrees Celsius and 277 milliliters of mercury. Okay, so we use this thing. Density is equal to pressure, the molecular, ooh, that's an ugly M. The molecular weight over RT. And I guess we gotta look at our units here. Okay, units are important for this one. Our pressure is 755 millimeters of mercury, but it's, oh wait, backwards. An atmosphere per 760 millimeters of mercury. Molecular weight for nitrogen is 28 grams per mole. R is 0.08206 liter atmosphere over mole Kelvin. Temperature is 398 Kelvin. That's 125 plus 273. And look at our units. So if you look at our units, the kelvins cancel, the moles, 1 over moles cancel, millimeters of mercury cancel, atmospheres cancel, and dimension-wise we have grams per liter. Okay, so that's our dimensionality in that. Oh, and here's nitrogen, 14. 14 times 2 is 28. Okay, so what does this then equal? So the answer is 0.852 grams per liter. Like, okay, that's nice. Well, that's actually really not that dense. So water, for instance, is 1,000 grams per liter. So a kilogram per liter. That's what water is, liquid water. This is less than 1,000th as dense as water. So why do we care? Well, you know, water or air is matter, but I can feel it as I'm holding my hand, but it's not that hard to move my arm in water. Or I'm sorry, air. But underwater, when you're swimming or moving around underwater, you got to really push that water out of the way. Why? You're pushing about 1,000 times as much matter out of the way. The other thing is, if you ever see, I mean, here on Maui, we've got the windmills going up West Maui. And can I see them? It's too cloudy right now. I can't see them. But they're big. And right now I'm in Kula, up Haleakala. You know, that's 50 miles away. And I can, maybe not 50, 30-ish miles away. And I can see them. If you've ever seen a hydroelectric plant, they're tiny. So especially the turbines in a hydroelectric plant, they're probably half the size of my house. So like that they're so small. Why are they so small? Because there's so much more matter in water than there is in air, and they turn much more easily. So, gee, we learned in chemistry today that air is thin, and water's thicker. Who would have thought that? Okay, so still talking about ideal gases. And ideal gases, so air, for instance, is a mixture of gases, mostly nitrogen and oxygen, a little bit of argon, a little bit of water vapor. But for multiple gases, you can look at this. So solving PV equals nRT, so nRT over V, or N pulled out there for the gas. And then the mixtures of gases. So when you have mixtures of gases, the pressure of each gas is just equal to the moles of each gas times RT divided by V. And the total pressure then is just the pressure of each gas. They just add together. So if you add 3 atmospheres of carbon dioxide with 3 atmospheres of oxygen, you get 6 atmospheres of the mixture. So that's how pressures work. And that right there is Dalton's law of partial pressures. And works very well for ideal gases. And then there's a mole fraction. Mole fraction is the amount of one species over the total number of moles. So for gases, it's usually shown as a Y. It's usually YA. And they do that, and if you ever do, so there's the Code of Federal Regulations, and there's certain laws called RCRA to deal with air pollution. It's always YA for gases, and engineering uses Y for gas pressure. I guess chemistry, for some reason. I'm both an engineer and a chemist. I guess just this level they use that, probably because, truth be told, freshman chemistry hasn't changed since about 1960. It's probably what Linus Pauling put, and we just haven't changed it yet. So, anyways, then the partial pressure of one species is just the mole fraction of that species times the total pressure. So let's do this. A 1 liter mixture of helium, neon, argon has a total pressure of 662 millimeters of mercury at 298 Kelvin. The partial pressure of helium is 341 millimeters of mercury. Partial pressure of neon is 112 millimeters of mercury. What's the mass of argon in the mixture? Okay, so we want the grams of argon. That's our unknown, the mass of argon. We're looking for that. And what are we given? So let's draw some pictures. I like pictures. So we have a 1 liter vessel. My 1 liter vessels all look like cubes. I'll even make it 3D for you. And in this vessel, we have a volume equals 1 liter. We have a total pressure equals 662 millimeters of mercury. And we have, we also have 1 liter, 298 Kelvin. And we have, and in here we have helium, neon, and argon. So pressure of the helium is 341. Pressure of the neon is 112. So we don't know the pressure of the argon. So how are we going to solve this problem? Well, we have to find out the partial pressure of argon, and from that we can figure out the moles of argon, and from that we can figure out the mass of argon. So let's do that. So pressure of argon, well, I guess maybe I should back up. The total pressure is going to be the pressure of helium plus the pressure of neon plus the pressure of argon, which implies pressure of argon is the total pressure minus the pressure of neon minus the pressure of helium. So pressure of argon equals 662 minus 341 minus 112, or I should say 112. And what is that? 662 minus 341 minus 112, 209. 209 millimeters of mercury. And PV equals nRT. N equals PV over RT. Maybe a little more space here. I'll move it over. Pressure, what is our pressure? Pressure is 662, so 662 millimeters of mercury. Convert to atmosphere is atmosphere over 760 mercury. Volume is 1 liter, that's easy. Over R, 0.08206. Liter, atmosphere, mole Kelvin. Temperature 298 Kelvin. Okay. So, and looking at our calculator, the number of moles of argon is 0.035. I want to write that, moles argon. So 0.035 moles argon times 40 grams argon per mole argon, and we get 1.42 grams argon. So, and that's what I want. Well, the mass of argon is in the mixture, 1.42. Okay. So what about air? I mentioned air. What is in air? Air is about 78% nitrogen, about 20.5, 21% oxygen, argon 0.9%, and then trace everything else. There's about 440 parts per million, seasonally cycling, rising, generally speaking, carbon dioxide in the atmosphere. Depends on where you're at. There tends to be about 1%-ish water vapor in the atmosphere. So this is dry air. Of course, there's more water in the air here in Hawaii than, say, Las Vegas. but there's more water in the air right now. In August as I record this video in Ohio, where I'm from. Man, August in Ohio, that's rough. All that humidity. So it just depends on where you're at, but it's more or less uniform across the globe here on Earth. So, and what's interesting, the atmosphere is mostly inert, but the Earth is weird because of the oxygen concentration. If you look at Mercury, the Mercury planet is 35% oxygen, but it has such a thin atmosphere, and that's 35% because this is being cooked by the sun. So it's not like you go, oh, I can go and breathe on Mercury. No, you can't. It's too thin. And it depends on where you're at. It's both hot and cold. If you sat in between the day and night of Mercury and then held your breath, you could live for a couple of minutes. But it's not a very good place to be. Okay, so that's what's in air. And so I guess we're going to partial pressure. Air is 78% nitrogen. What's the partial pressure? It's that. Okay, but let's talk a little bit about oxygen. So we are pretty good at being, for humans, this is humans' response to oxygen, we're pretty good at sea level. We kind of like being at sea level. If you go up in altitude, you can get to the point where you don't like it. I tend to get altitude sickness. Above 8,000 feet, I'm not a very happy camper. Although I've been up higher. I've been as high as 14,000 feet. I really don't like that. But if you get to a point like 0.1 oxygen concentration, that's hypoxia, then it's just your brain starts to shut down. So that's why they have the oxygen masks in plane. In case of the decompression, you can grab it and breathe. Okay, and then 100% oxygen. So we can breathe pure oxygen, and the highest we can go is about 1.4 atmospheres. So why do we care? What's the point in this? It's because of scuba diving. So if you are scuba diving using air, if you go 30 meters, 100 feet underwater, your oxygen concentration pressure is 0.84 atmospheres. And then if you go further, if you keep on going further, right, say you double your depth there, the partial pressure of oxygen is, it's going to be 7 atmospheres. And 7 times 0.2 to 0.21 is 1.47. So you're getting close to it says maximum absorption. You're getting close to that number there. So what do you do if you want to go deeper? You have to have a lower concentration of oxygen. You have different tanks, and specifically they typically use something called heliox. You have helium combined with oxygen. And why would you use helium? Helium tends not to dissolve in the blood. Well, nitrogen can dissolve in the blood, and there's a condition called nitrogen narcosis, where nitrogen acts like a narcotic. When you go down deep enough, we're spinning around. There we go. There we go. It's like a barrel roll, Google barrel roll there, chemistry barrel roll. So you can get nitrogen narcosis from the levels of nitrogen in your blood. The other thing is you can get a condition called the bends. It's called the bends. They actually discovered that in the construction of the Brooklyn Bridge. Workers are going underground and they work in the dark. And like if I was a worker doing that, I'd want to get out of there as soon as my shift was over. So when the shift was over, they got up as fast as they could. And some people, when they're like, oh, I'm out of that deep, dark chasm, and when they got up, like, oh, I can't move. Sit up. Like, oh, I can't. I have the bends. Because what happens is nitrogen bubbles accumulate around your joints. And I've never had it. Apparently, it's very, very painful. So that's what's called the bends. And how do you avoid getting the bends? Go up pressures very slowly, or in the case of deep diving, you can use heliox, where helium does not really, it does a little bit, but doesn't readily dissolve in water all that much. So it diffuses much faster. So it's better. That's better to have that mixture. But this, of course, is more expensive. So, okay, we're done with this video. See you next time.